Okay, in this podcast we're going to talk about the kinetic molecular theory, and this is the model that helps us understand gas behavior and what happens as we change conditions. Alright, so there are main tenets of the kinetic molecular theory, also called KMT, is that gases consist of large numbers of molecules that are continuous random motion. Now when we say random motion, it doesn't mean that they dance and spin and they twirl around, but they will go basically in a straight line path until they hit something, and when they hit something they get deflected. So they're always running into something, especially the walls of whatever container they're in, be it a room or a box or a cylinder. Okay. The combined volume of all the molecules of a gas is negligible relative to the total volume in which the gas is contained. So what that means is if I have gases in a container, they are so tiny and they are so far apart that the volume they take up is insignificant compared to the total volume. Okay, makes sense. Attractive and repulsive forces between gas molecules are negligible. So what that says is there's no attraction between these gas molecules, and because there's no attraction, there is no slowing down when they hit each other or when they hit something else. So that there's nothing causing this to slow down. So another way of saying this is that the collisions are elastic, which means that no energy is lost. So they don't slow down when they hit each other, or if they hit the side of the containers. All right, so we also know that energy can be transferred between molecules during collisions, right? So one molecule hits another, and that transfers the energy, right? And that can hit another, and that transfers the energy. But the average kinetic energy doesn't change with time as long as the temperature is the same. So if I think about a gas, let's say at 0 degrees C, and I look at the speed of the molecules, I can plot the distribution of that speed, and they're not all going to be the same. Now their average is going to be consistent though. So there'll be some that are moving very, very slow, and there'll be others that are moving quite a bit faster. But on average, their speed's going to be the same. Now if I increase the temperature, I end up with a wider distribution that because I have the same amount of gas, the amount of space, the area under the curve is the same, but the distribution of those particles is spread further, and then I end up with a higher average and a bigger tail, right? As it spreads out, the tail becomes larger, and I have more particles at that higher speed. We also know that the average kinetic energy of molecules is proportional to their absolute temperature. So the higher the temperature, the higher the kinetic energy. Makes sense? The temperature is a reflection of that energy. Alright, so let's take a look at what this means in terms of a real gas, or an ideal gas. A sample of oxygen is compressed to a smaller volume at constant temperature. So here I have a gas. Let's say it's in a cylinder. I'm just not drawing this very well, right? And I take that same cylinder, I don't know why my stuff's coming out crooked, and I push the plunger down so it's taken up half as much space for the same gas. What effect does this have on the average kinetic energy of the oxygen molecules? So what we said is the temperature is not changed. So if the temperature is not changed, the speed of the particles is not going to change, because temperature is a reflection of the speed. So the speed will be the same. What happens to the total number? All right, B, what happens? Okay, so I screwed that one up. Speed question was B. The A question was, what happens to the kinetic energy of the molecules? And the answer is nothing. Again, because the temperature hasn't changed, so my energy hasn't changed. So energy is the same, speed is the same. C is what happens to the total number of collisions of oxygen molecules with the container walls per unit of time. Alright, so here I have, let's say I have 3 particles in here and I have 3 particles in here. There is less container wall to strike for the same number of particles, so my number of collisions is going to go up. And then D is what happens to the number of collisions within a unit area of wall per time. So that says not the whole wall, but let's say a piece of the wall, this area here. What happens to the number of collisions? Well, again, I've got particles condensed in smaller amount of space, so that also will cause more collisions. Now, we can look at what happens to that distribution and calculate the root mean squared, which is that U you saw on the Maxwell-Boltzmann chart, right? We can calculate what that's going to be at any given temperature, and the speed is going to be inversely related to the molar mass of the substance. So the bigger the molar mass, the bigger the molecule, the slower it's going to move. That's basically what this is saying. So we can actually calculate the root mean square velocity, which is the indication of the average speed of the molecules, using this equation. So U indicates the velocity of the molecules. R, because we are talking about energy, we're talking about speed related to energy, we need to use the R that has joules in it, the energy term. So that's going to be 8.314 joules. Temperature, of course, will be in Kelvin. And the big thing you got to remember, this is not what you would expect, is the molar mass has to be in kilograms. It has to be in kilograms. Because when I'm talking about energy, again, kinetic energy is 1/2 mv squared. The m is kilograms. Okay, so again, we're talking about energy, so I need to use kilograms. Okay. Gas at 25 degrees C. Okay, so we know the root mean squared velocity is the square root of 3RT over the molar mass. And so that's going to be, let me just put it down here, 3 times 8.314 times 25C is 298. Okay, right? I'm going to divide that by the molar mass in kilograms. So the molar mass of helium is 4.00 grams, so I'm going to make it 4.00 times 10 to the minus 3 kilograms. Okay. And I need to take the square root of all that. So first I'm going to figure out what that is inside the square root. So it's 3 times 8.31, whoops, 314 times 298 equals, divided by 4 second EE negative 3, and I get that. And now I need to take the square root of that, so I'm going to do second square root, and I'm going to use my arrow to go up and pick that number up, put it in the square root, calculate it, and I get 1.1363, and let me see, I want looks like 2 or 3 sig figs, so it's 136 meters per second, which would be my velocity units. Alright, not too bad. Okay, so let's talk about this term of fusion. A fusion is like diffusion. If I have a gas in a container and I open the lid, that gas is going to diffuse. It's going to move out and spread apart. If fusion is similar to that, but what I have here is I make a little hole, And that hole is a spot where particles, if they have the right orientation and the right speed, will come out. Okay, so we're going to be looking at what's the rate of effusion. Alright, so we can look at, for instance, the difference of the rates of effusion for helium and nitrogen. And as you would imagine, the nitrogen is a bigger molecule, so it is going to effuse more slowly than a helium would. Okay? So a helium is, if I fill two balloons, one with helium and one with nitrogen, the one with helium is going to deflate faster because it's going to come out these tiny little gaps that are in the balloon. So we said diffusion is the spreading of a substance throughout a space, right? So Graham's law allows us to compare the effusion of one gas to another. So for the first gas, kinetic energy is going to be 1/2 mv squared. For the second gas, energy is going to be 1/2 mv squared. So if I rearrange this, I get the mass of one over the mass of the other is equal to the velocity squared of one over the velocity squared of the other. Okay, so don't forget I got gas 1 here and gas 2 here. They invert when I get to the molar mass on this side. Okay, so here's the Graham's law. It's on the equation sheet. Might get a question on the multiple choice though, so you've got to understand conceptually that the bigger the molar mass, the more slowly it will effuse. The other really important thing when you're doing equations or you're doing solving problems is you got to remember that rate is not the same as time. So rate is the change in something over the change in time. So a lot of times we're talking about change in concentration, let's say change in molarity. So don't confuse time for rate. Alright, so an unknown gas compound of a homonuclear diatomic molecule, which means it's something like H2 or O2, effuses at a rate only 0.355 times that of oxygen at the same temperature. Alright, and calculate the molar mass of the unknown and identify it. Okay, so what I know is the rate of some gas over the rate of oxygen is 0.355. Okay, so it's 0.355. And I know that it's equal to the square root of the molar mass of oxygen over the square root of the molar mass of this gas. So let's just rearrange the equation first because I want to solve for the molar mass of the gas. So 0.355. Actually, let's do this. In order to solve for this, I got to square everything. Square this, square this, square this. So I end up with 0.355 times the molar mass of the gas is equal to the molar mass of oxygen. So when I square this, I just get rid of this square root, right? So my molar mass of my gas is going to be my molar mass of oxygen divided by, this should be squared, 0.355 squared. So I know my molar mass of oxygen is 32, right? And if I put that over 0.355 squared, let's see what we get. Alright, so I have 32 divide by, I'm going to put in parentheses, 0.355 x squared, close my parentheses, and I get 253. Now this is going to be 0.9 grams per mole. Okay, so what I know is this is a diatomic gas. It told me here that in the problem. So I got to divide this. If I divide this by 2, I get about 127 grams per mole. And if I look at the periodic table, well, that matches up quite nicely with iodine, which has a molar mass of 126.9. So the gas in question is I2. The last thing we want to talk about is, so we've been talking about KMT and ideal gases, but in fact most gases are not ideal, and their behavior is different than what would be predicted. So here I have a plot of pressure versus number of moles I would expect solving for moles, right? And if I have an ideal gas, the results should be on this line. But in fact, you can see that they are way off the line. Okay, so in the real world, the behavior of gases only conforms at relatively high temperature and relatively low pressure. So if I have high temperature, that means my particles are moving really fast. And if I have low pressure, then they're not very compressed, right? So they're going to be free to move about. So, the further apart the gases are and the faster they're moving, the more ideal their behavior, right? But if I compress them, if I put pressure on them, and I slow them down, then they move away from ideal gas behavior, okay? So even a given gas, this is just one gas, at different temperatures behaves quite differently. So why is that? Well, the assumptions made in KMT are that there's negligible volume of gases between molecules. Starts to change if I put pressure on and bring them together, right? Now their volume they take up is less negligible, right? And the other thing that's different than what KMT says is in fact there is some attraction between gas molecules, okay? And that attraction, it usually comes from London dispersion forces, and as we know, the more electrons a compound has, the larger the London dispersion forces, because the larger skewing of the electron cloud that you can have. So there's going to be more attraction when you have bigger molecules, right? Because bigger molecules means more electrons. Okay? And the slower they're moving, the more attraction they can have, right? So if they're lower temperature and higher pressure pushing them together, those attractions will be greater, and the movement from ideal behavior shifts. So there is a equation called the van der Waals equation, which can be used for adjusting for this non-ideal behavior. Okay, and this equation, which looks like a mess, this is on the equation sheet, and what you need to know is when you move away from ideal behavior, you're adding something to the pressure. So pressure is going up, and you're subtracting something from your volume, right? So your volume's going to go down, and that makes sense. If you add pressure, you're causing the space to decompress or to compress, and it's going to go down. And there's tables, and you'd have to be given this data in order to calculate this, but there's tables that tell you what this A factor adjustment are and what the B factor adjustment are, and they're different for each gas. Okay, so let's take a look at using this equation, and it's not as bad as it looks. It's just rearranging the equation and plugging the information in. Okay. Alright, so if I have 1 mole of an ideal gas confined to 22.4 liters at 0 C, it would exert a pressure of 1 atmosphere. If I use the van der Waals equation and the constants in the table that we just looked at, estimate the pressure exerted by 1 mole of this chlorine gas, it's chlorine specifically, in 22.4 liters at 0 C. So the equation on the previous page said P plus N, which is moles squared A, over the volume squared, that's the pressure adjustment, times my volume, which is minus moles, times this B factor, that's specific, right, to different substances is nRT. Alright, so in this case, I am trying to solve for pressure, so in order to do that, I'm going to do some rearranging. So I'm going to divide both sides by V minus NB, and I end up with P plus N squared A over V squared is nRT, and if I want to solve for P, I'm going to subtract this from this side. I end up with nRT minus N squared A over V squared. And now it's just a matter of plugging the information in. So nice that I have 1 mole. My R is, because I am not dealing with velocity here, I am using my 0.08 liters atmospheres, right? Liters atmospheres over moles K. My A, I can look up on the table. This is chlorine, so I've got to find out what the, I'm sorry, I'm still doing T. So T is 0 degrees C, so I'm at 273. Okay, so that's this, right? Minus N squared. It's nice that N squared, N is 1, so N squared is 1, times my A, and my A in the table is, I missed something here. This, I need this term here. Sorry about that. Alright, so my volume is, let me see, 22.41 liters, minus moles, which is 1. My B I can look up on the table for oxygen, and it's 0.0562. And I'm going to subtract from that, so that I got this whole thing here, which I'm going to subtract. This is a minus, not an equals. Minus N squared, which is 1, times A, and A is, I look up on the table for chlorine, and it's 6.49, and I put that over my volume squared, and my volume is 22.41 squared. So it looks like a beast, but in fact this is relatively simple math once you just plug it in, and if I do plug all that in, I end up with 0.99 ATM. Okay.